Hey everyone, Sin here. Today we're going to do some engineering and stuff. Welcome to the final part in our LabVIEW SONAR series. In this video we're going to go over the final SONAR configuration, which has been the culmination of the last few videos. I'll go over the final system configuration and circuit schematic. We'll also go through the LabVIEW code and methods to implement the user interface and polar plot, all of which will be available on my GitHub. The parts list will also be in the description so you can build it yourself. Let's get into it. So the final configuration of the circuit has changed since we last looked at it. In the earlier configurations I was powering the servo from the Arduino 5V rail, but over time I found this to be problematic and unreliable. It is also not best practice despite many examples showing it this way. The main issue with this is that the servo was injecting noise into the system when under load, which resulted in unreliable results from the ultrasonic sensor and glitches in the code. I'll touch on this more in a bit. For now, let's go over the breadboard schematic. As you can see, we're now powering the servo from a separate power supply. I'm using the MB102 breadboard power supply for this task, which is good enough, with a 3.3 or 5V selectable rail and 700 mA output current. Make sure you use a common ground when you're using more than one power supply. This is so you don't unnecessarily create ground loops in your circuit, and you can see here the negative rail of the supply is connected to the ground of the Arduino. You'll also notice the inclusion of capacitors across the power rail of the breadboard power supply and the PWM signal line. This will be important later. The ultrasonic sensor configuration stays the same. It is powered by the Arduino 5V rail and connects directly to pin 7 and pin 8. Let's now look at a detailed pinout schematic for the system. It's the same as a breadboard schematic but in a more professional format. This gives a much clearer and simpler view of what's going on in our circuit. When powering the servo via the Arduino 5V rail, I often notice random fluctuations in my measurements when no objects were present. I initially assumed this was due to the accuracy of the ultrasonic sensor and reflections being picked up during the sweeping arc, which is partially true. But this unusual behavior became more apparent when testing the system while making this video. The code would sporadically slow down, which meant something in LabVIEW was timing out, then pick back up to normal speeds like nothing happened, despite making no changes to the code or hardware and running perfectly fine on previous tests. After a bit of research, I concluded it was due to the noise generated by the servo under load. So I googled the no-load and stall currents of the servo and found these two specifications. On the SG90 page, you can see we have a current consumption of 550 mA for the SG90. Now I'm assuming that that's a loaded current, whereas for the FS90, which is quoted as having similar form and function to the SG90, we have an idle current of 10 mA, a no load current of 100 mA, and a stall current of 700 mA. So it's easy to assume under moderate load the servo is drawing anywhere from 100 to 550 mA. Now knowing this, can the Arduino handle this current demand while keeping itself powered sufficiently? Well, kind of. I'm powering my Arduino via a USB 2.0 port, which is rated for a 500 mA max output. Looking at the specifications for the Arduino, we can assume the unit itself draws less than 100 mA. The 5V rail is rated at a maximum of 400 mA when powered by USB, so that leaves us with less than the required top end of the operational current range for the servo, which is 550 mA, let alone the stall current of 700 mA. This will be an issue under sudden loads, as the Arduino may not always be able to provide the required current, and as a result you may get glitches in your microcontroller and inject noise back through the power rails or signal lines. Digital circuitry doesn't like this. So the obvious way to resolve this is to power the servo from an external power supply that can provide the required current. In our case, the MB102 supply is rated for 700 mA, which should be enough for our basic sweep and minor load. And as further good practice, we are using bypass capacitors to reduce the noise on the signal line and power lines, which you can see in the Pinout Diagram we've been staring at through this explanation. Make sure you observe the polarity of the capacitors and connect them accordingly. These essentially act as a low-pass filter, shunting any high-frequency noise that may creep in. They also act as a reservoir for sudden power demands. Note also they should be placed as close as possible to each rail. This is to keep the inductance and ESR as low as possible so we don't introduce other issues which is outside the scope of this video. So in conclusion, if you absolutely must, you can power a servo using the Arduino, maybe for a quick test or prototype, but make sure you use a bypass capacitor. Otherwise, it's best practice to power the servos externally with supplies that can handle the stall and operational current demands. Since we've been talking so much about noise, let's demonstrate the difference between the two configurations. On the top, we're running the servo and ultrasonic sensor off the Arduino 5V rail, and on the bottom we are running the servo off the breadboard power supply and the ultrasonic sensor directly from the Arduino. The test configuration for each is identical, and the sweep clips shown are synced so you can observe how each configuration performs. If we observe and compare, you may notice the top sweep runs slightly slower and noise is being picked up over the same sweeping arc. This noise is apparent in the form of the random dots you are seeing on the polar plot. However, over the same arc, nothing appears on the bottom configuration. I will flag the noise as it appears. You'll also notice over time the top plot is slowing down and slightly falling behind the bottom plot, which is much smoother and stable. By the end of the sweep, we see that the code for the top configuration has fallen behind by about 7 degrees. So the code that's running in the backend is executing slower for the top configuration than the bottom configuration, even though it's the same code. We also observe how the configuration on the bottom is smooth and stable and only returns the object detected. Now that the hardware side is finalized, let's get into the actual LabVIEW code. Looking at the front panel, nothing exciting is going on yet. We have of course our string indicator for our device name to let us know if we connect successfully to our Arduino. We have our stop Boolean control button. Here we have a Boolean indicator, more specifically a square LED indicator. To access this, simply right click the front panel and under modern, select Boolean, then square LED. If we click it, we see the states change, and it warns us when an object is detected. To alter your Boolean control states text, simply right-click, Properties. Under Colors, you can choose what color the on and off state displays. Under Show Boolean Text, you can set what text is displayed for each state. Note, if you want to display text for both the on and off state, you need to make sure the multiple strings checkbox is ticked. Otherwise, by default, only the off text is enabled. And to the right, you can also select the text color you want to display. Next we have a 2D picture indicator, where we will be drawing our sonar. More on this later. And finally, we have two numeric indicators that show the distance to the object in centimeters and the angle of the servo arm relative to the detected object in degrees. Now, if you're interested in customizing your indicator color palette as I have here, it is as simple as doing the following. Under View, select Tools Palette, then select the Set Color tool. Now, if you right click on anything on your front panel, a color palette will appear which will let you select the color of the object you select. Just note, it's a bit fidgety when you want to select things like the indicator borders. You must be spot on with the cursor. That's it for the front panel. Let's get into the block diagram. So the first thing you'll notice, of course, is that we now have two while loops. That's because I've implemented a popular architecture called the producer-consumer architecture. Do we need this architecture to implement the sonar? No, but it's much cleaner and is one of my favorite architectures in LabVIEW that I've used in countless projects. If you master it, you can extend it to the queued messaged handler architecture, which is very powerful for application development, but that's a topic for another video. So what's the producer-consumer architecture? Well, in short, the first loop is where we produce the data we want to process, usually but not always in a deterministic fashion. For example, reading a voltage signal from a data acquisition device tends to produce a term, and the bottom loop is where we process or consume the data, generally in a non-deterministic fashion, for example plotting a graph or writing to file, hence the consumer term. The primary advantage of this is both loops can run in parallel and at different rates. The way this is done is by utilizing the queue functions to achieve the synchronization between two or more loops. One tip to remember is you need one queue per consumer loop, so if you intend to have multiple consumers, you'll require multiple queues. Queues in LabVIEW are FIFO and are lossless, so if consumption is slower than the production, the queue will eventually become full. The producer code will be forced to wait until the consumer has dequeued an element before a new element can be queued up. By default, queue sizes are set to unlimited, so this will bring into play other factors like memory size. Even though the queue size may be unlimited, the rate at which you consume the data will be a bottleneck in your application. This is important to consider, especially if you have a time-critical application. If you want to set up a producer-consumer application from scratch, simply go to File, New, from Template, Design Patterns, Producer-Consumer Design Pattern Data. This will create a nice template for you to expand on. If we examine the SONAR code, the top loop is the same as our previous projects, except now we are enqueuing distance and angle data and sending it to the consumer loop so we can plot our nice parallel plot. I won't go over the Arduino and sensor code because you can get the full explanation in my other videos. I will have a go over how we set up a queue. To access the queue functions, you want to right click the block diagram, go to synchronization, and then queue operations. Under this palette, you have all the queue functions available to you. Here we first initialize the queue and specify the data type. This tells the queue what data type will be enqueuing. Here it's a cluster of two elements, the angle and distance. Then we pass the queue reference to the enqueue element function, which is expecting a cluster as the data type. If you look here, we are bundling by name two pieces of data and using a cluster constant from before as the input cluster. This is good practice, so you don't have to keep copying the cluster constant, and it allows us to select the data by name, so it's clearer when reading the code. Now this is done, every loop iteration, the data from the cluster will be placed in our queue, ready to be processed by our consumer loop. Finally, we release the queue, close the reference to it, and free the memory resources allocated to it. I hope you have noticed a theme here. Most things in LabVIEW are set up under the same logic. You configure the function, you act on the function, then you close your reference to the function. This is applicable to many functions in LabVIEW, especially when setting up hardware or communications. We then take the queue reference, pass it to the consumer loop, and dequeue the elements using the dequeue elements function, which in this case produces a cluster of the type we specified when we set up the queue. We then take this data, unbundle it, and now have access to our angle and distance data for processing. Now, before I describe how I'm generating my parallel plot for the SONAR, I'd like to acknowledge the inspiration for it, which came from this National Instruments forum post on how to design a radar VI. There are some good examples here, and it's what I use to build my code off. So I encourage you to check out the post and the contributions from those who posted. The link will be down below in the description. My approach is different from those examples in the posts, however, as I'm plotting on a parallel plot using r and theta values, which are distance and angle measurements respectively. This makes plotting it much easier, as I can change the parallel plot settings and scale of the 2D picture without having to write code to scale and map coordinates, as this is handled internally by the parallel plot functions. This is a different approach to the examples in the post, as they most often represent the object by drawing a point on the 2D picture when using Cartesian coordinates. This then needs to be scaled to correspond to the picture size when an object is detected, so the dot location is relative to the distance and angle as it is in the polar coordinates. And given we already have the polar coordinate information, plotting directly to a polar grid is a more viable option, as it provides more accurate real-time information on object position relative to the sensor, as we are essentially now plotting the outline of the reflected surface as opposed to representing it as a blip. The only extra work is the configuration of the polar plot and replicating a radar aesthetic. So how are we generating this polar plot to represent our SONAR data? If we start on the left of the consumer loop, we are initializing the 2D picture data and image data cluster with empty constants. You can generate constants simply by right-clicking on the input of the function you're using and selecting Create Constant. Notice the image data constant is initializing a shift register. This is because after each loop iteration we want to update our image data instead of discarding it, to replicate the phosphorus ghosting effect on our picture plot that's reminiscent of old radar displays. We enter the loop and dequeue our data. which is then unbundled to give access to the angle and distance values. From top to bottom, first we have a property node for the 2D picture, which is outputting the 2D picture's draw area size, which is a cluster containing the height and width. This is required for scaling purposes for the polar plot on the 2D picture. Property nodes are a great tool for controlling and reading front panel properties. To create one, simply right-click a control, create, property node, then select the attribute you want to read or control. Our data cluster is then unbundled and passed to the sub-VI, processing and plotting. The draw flatten pixmac VI is initially taking in our 2D picture and image constants to initialize an empty picture. This picture is then passed through the loop for further processing in our sub-VI. Its image data is modified each loop iteration and passed through the shift register. This allows us to replicate the ghosting effect, where the needle and point slowly fade after each increment of the needle. We then start setting up our polar plot. Now this is done in a few steps. We first set the polar graph attributes with a cluster constant. This is done as it doesn't change and is kept inside the loop for neatness. If we expand this constant and examine the properties, we can set the max and min value for the polar plot. These correspond to the ultrasonic sensor distances range we want to measure. 2 cm is the minimum distance the sensor can measure, and I'm hard limiting it to 40 cm for the maximum value so we can ignore reflections outside the test area. The clip to min boolean, which is set to true here, all this does is clip your value to the minimum if it goes outside your specified min or max range. The log boolean set to false here because we don't want a logarithmic scale. The grid and plot color for setting the polar grid and plot colors, of course. We set the plot color to green here, so everything will be plotted in green unless we otherwise specify. This sets the sonar needle color. The format and precision values, which are set to decimal and 0 in my case, because I don't care about reading the values from the plot. They will be displayed in our indicators. And lastly, the most important attribute, the visible section. This value will set what quadrant of the polar plot will be visible. Here we can see the list of options, and in our case, 4 represents displaying quadrants 1 and 2. This will represent our 0 to 180 degree sweep nicely. Next, we set up drawing the sweeping needle on the polar plot. We generate the polar plot data for the line each loop iteration by constructing an 1D array of cluster values which represent the polar quadrants. The origin cluster represents 0, 0, and the bundled values represent the value 40 theta. The magnitude is set to 40, the maximum value of the polar plot, so the point is always on the edge of the grid. The theta value, which is coming from our Q, is the angle of our servo arm. This enables the needle to sweep in sync with the servo's rotation. We then plot a line between these 2 points to generate the sweeping needle. This is handled by the line sub-VI, which if we open it and its block diagram, we can examine what's going on. It's simple. We pass in the picture reference, the polar array data, the draw area size array, and lastly the polar graph attributes. Then we tell the polar plot VI to plot a line and specify its size. It's that easy. With this information, the polar plot VI will take care of all the scaling for you. Next, we handle drawing the polar grid onto the 2D picture, which is handled by our grid sub-VI. Similarly, if we examine this block diagram, it's pretty simple, with just a little more going on. Again, we're passing the picture reference and polar attributes, but here you can see we are doing some arithmetic. The origin for this code snippet is from the polar plot VI. If we examine its block code, you can see here it's being passed to the polar grid sub-VI. I believe this is just for making sure the 2D picture dimensions are rectangular. Next, we move on to the object detection logic and sub-VI for plotting points on the polar plot. If we start with the Boolean logic, all we're doing is using the in-range coerce function to make sure only the detected points from our ultrasonic sensor within our max and min range are logged to the polar plot, and if they are outside this range, we coerce the value to the minimum value. We then use the Boolean value to plot the detected object on the polar plot. So if an object is detected and within the range, we return true and plot. If it is false, we plot nothing and move forward in the loop. This is handled by the case structure here. Now if we examine the true case, we're passing our data array to the point sub-VI, which is responsible for plotting the detected point on the polar plot. If we examine the sub-VI, this is straightforward. We take in all the picture references, polar plot data and data array and pass it into the polar data sub-VI, which is responsible for scaling our data onto the polar plot. We simply specify a point to be plotted and the size of the point. Note we also change the color for the polar plot using the bundle by name function below, as you can see, to red. Next we can see our indicators, where we are passing the queued data to for display on the front panel. We then take the picture, convert it back to Pixmac to access the image data cluster, and then use the in-place element structure to multiply the image array by a scale factor less than 1. This reduces the intensity of the image by that factor. For example, if it's 0.5, the intensity will be halved. This allows the replication of the radar display, where the trace decays over time, as the previous image is still present through the shift register on the next loop iteration, with a reduced intensity, and as we repeat this, we get a nice decay effect of the needle and points. Lastly, we finally plot the data on our 2D picture, and that's it for our SONAR project. I hope you enjoyed the journey. All the code is available on my GitHub, which I will link below. Thanks for watching my video. If you enjoyed this, please like, comment, subscribe, and I'll see you in the next part.